Our sun accounts for 99.8% of all the mass in the solar system. To comprehend the extremes of the universe, we must shrink that massive star down to the physical size of a single 1 millimeter grain of sand. Even at that microscopic scale, gravity governs everything. The absolute extreme of that gravitational pull is a black hole, a region in space where matter is packed so densely that nothing, not even light, can escape its grip. When massive stars collapse at the end of their lives, they leave behind stellar mass black holes. These dense cores weigh anywhere from 3 to 100 times the mass of our sun. We often view these stellar black holes as the apex of cosmic extremes. In reality, they are merely the smallest data points at the very bottom of a much larger cosmic scale. To find heavier masses, we have to look past isolated stars and travel inward toward the dense center of the Milky Way galaxy. Lurking at our galactic core is Sagittarius A star. This is a supermassive black hole, weighing an estimated 4.3 million solar masses. Its event horizon, the boundary of no return, is 25 million kilometers across. You could fit that entire dark sphere comfortably in the empty space between Earth and the Sun. Yet, as astronomers scan the deep universe, they have identified a rare, heavier tier of objects. They call these ultramassive black holes. These entities average 10,000 times the mass of a typical supermassive black hole. They test the mathematical limits of how large a single object can grow before breaking our current models of physics. In 1957, astronomers at the Tonantzintla Observatory in Mexico were mapping faint blue stars. They recorded a distant, seemingly unremarkable blue dot and logged it as entry 618. 13 years later, a survey detected intense radio emissions coming from that exact spot. TON 618 was identified as a quasar, an active galactic nucleus blasting out radiation 140 trillion times brighter than our sun. That intense glare completely hides the host galaxy and the black hole powering it. To figure out what lay inside, scientists had to analyze the quasar's light spectrum, specifically looking at how wide its emission lines were stretched. Those stretched lines indicated that superheated gas was spiraling inward at 10,500 kilometers per second. By measuring that velocity, astronomers could calculate the exact gravitational force required to keep that material in orbit. The math revealed an unfathomable center. TON 618 is a single black hole weighing 66 billion solar masses. The brightest light we can see in the universe is fueled by the heaviest dark mass on record. If you fall toward TON 618, you plunge through a violently hot accretion disk, a chaotic vortex spinning near the speed of light. This diagram illustrates a black hole's event horizon. The distance to this boundary is the Schwarzschild radius, where escape velocity exceeds light speed. For TON 618, this radius spans 390 billion kilometers. Our planetary system out to Neptune would fit inside 40 times over. Crossing that threshold means stepping into a void exponentially larger than our planetary neighborhood. Once inside, not a single photon of light will ever escape. The light we are observing from TON 618 took 10.4 billion years to reach Earth. We are seeing this quasar exactly as it existed when the universe was only a few billion years old. Assembling a 66 billion solar mass black hole that early in cosmic history challenges our current models of astrophysics. There simply shouldn't have been enough time or available matter for a single object to grow this large so quickly. Which brings us back to our 1 millimeter grain of sand. If our sun is that single grain, the Earth is a microscopic speck orbiting exactly 10 centimeters away. On that exact same scale, TON 618 would be a massive, solid sphere roughly 280 meters wide. Or pictured another way, imagine that single grain of sand sitting at the base of the Chrysler Building. Out in the Canes Venatici constellation, a singularity exists that is so massive, it reduces our entire solar system to a subatomic particle. It is a quiet reminder of exactly how small we are in the vast architecture of the